Good morning, everyone. I'm Eric Ostby. I'm Vice President of Product Management at Rigetti. Excited to be here with all of you today and want to share a couple comments on why we think the U.S. continued leadership in QIS is really critical. So just show here some of the partners that we have across the agencies and government labs. So part of the SQMS Center for Quantum Computing. Next slide. Great. So QS, we've heard from a couple of our speakers how critical it is in the applications it can open up. Just wanted to reinforce that it is, I think, seen as probably the leading technology innovation worldwide across countries and geographies. And it typically breaks down into three areas: quantum computing, quantum networking, quantum sensors, but there's more to come. So just showed here a couple of the application areas. Data security is really critical, of course, forward-looking to protect our data, and quantum networks are starting to come out and be discussed, which is exciting to see and will be really critical for running a utility scale quantum computer. But more fields are coming. So these are the typical three, but I'd say let's keep our minds open for new areas of applications. Next slide. We're expecting quantum computing to really transform economies around the world, and that's why it's so critical that the US continue to lead in this area, not only for national security reasons, but also for the applications and benefits to humanity and our citizens. And here's just a couple of the many application areas that we expect to come out in quantum chemistry, cybersecurity, and drug discovery, et cetera. It really is a human endeavor. It's a global challenge and opportunity, and it's important that we collaborate, but we also can lead the world, because the US is commonly looked at as a technology leader, and other countries will base their budgets and their programs off of what we do. So we have a responsibility and an opportunity to continue that leadership. Next slide. There's been a lot of progress. I'll focus today on quantum computing. So Rigetti is a full stack quantum computing company, now public, and that's one of the great progresses that we've seen in the past few years. Quantum computing was first conceived in 1981 by Richard Feynman in a talk at MIT, where he really thought, what's the best way to simulate nature is to actually use a quantum computer, because it's based on quantum physics. And there's been slow and steady progress since then, since the 80s. But really, the last 5 years, we've seen incredible acceleration in the progress, which is exciting. So 2016, IBM launched their first quantum cloud, which is exciting to give that access to users around the world. Rigetti has the first domestic quantum fab, captive fab, back in 2017 that was launched. The quantum initiative we've been talking about today in 2018 was a seminal moment for our country and for the world. In 2019, I think a turning point for many, including quantum skeptics, was the Beyond Classical experiment that Google did that showed that quantum computation is real and it's scaling. You can do a computation that's faster on a quantum computer than a supercomputer. In 2020, we had the launch of the 5 incredible centers with the DOE, and Rigetti's part of SQMS, which is great. In 2021, Rigetti announced the first multi-chip processor, and we're seeing that that's becoming an industry standard approach to how you scale these computers. And now we have a couple of quantum computing companies in the marketplace that shows that this is becoming a reality and people are investing and growing behind it. And there's lots more to come. I think the focus of the next few years is really on increasing that computational scale. We heard from some of the speakers about those problems that are being tackled and scaling those up. Better fidelity, better accuracy, so making these quantum computers that are a bit noisy today more accurate as you head towards fault tolerance, where you can maintain the state of the quantum computer, and utility, so exploring how we can find a quantum advantage. And I just show a shot here of how it's really critical that we see that we're making steady progress here, similar to some of the missions in the past. And I think where we're at is we've launched some rockets in quantum computing, and we're looking to get into orbit, which is stable quantum computation, and then exploring the galaxies where we're looking for those applications that we know we're going to find. Next slide. There's been a ton of investment. It's been growing in the field, and it needs to stay steady. Show here just a snapshot of some of the countries around the world. The estimates there are about $2 billion annually spent across public and private in quantum computing, with a good acceleration the last few years. And so this is valuable. It's increasing support. It's across the QIS areas, and we look forward to seeing it continue. Next slide. And quantum manufacturing is a great opportunity for the US to continue leadership. So in the semiconductor industry, somehow, unfortunately, we let that really technology go abroad. And now we're looking to bring it back with chip shortages, right? So here we are in quantum computing, and we have, I'd say, a strong leadership position in the US, a number of quantum fabs and foundries. And this is really critical for the future of quantum computing. And the US needs to continue this leadership, because you cannot build a quantum computer without a strong chip manufacturing. These are very different devices that you can't make in a normal fab. They're very sensitive to any noise or contamination. And so you need to have a dedicated facility to really scale up and reach the performance levels you need for utility. So the US has a leadership position. It's important to continue that, to enable the finding of building the quantum computer and finding those applications. And so it's amazing to see that we have this, and let's support and let's incubate and retain this. Just wanted to give an example. Quantum computers today has thousands of individual parts. You've seen some of the pictures of the crash stats, and each one of these is typically a really critical failure point. So we really need to have a strong supply chain in quantum computing. And we have that position now in many areas of the stack, and let's retain that. Next slide. The workforce is come up today, and is a really critical area to continue leadership, and the federal programs have helped in that area by stimulating investments and growth of the students. So I just wanted to say, let's continue this. It's a tight workforce. There's still a lack of trained workers, and it's good to see it's expanding from primarily PhD scientists further on to more broad backgrounds. So keep supporting this. Figure out ways to retain the top scientists, to encourage other students to enter the field, and train professionals that are more established in their career to come into quantum computing or quantum information sciences. And just a reminder, the US has a gap in terms of the STEM scientists that we graduate each year. So this is a challenge, and I think it's becoming harder to attract externally to bring top scientists in. So incubating, growing people in the US and the students is really critical. Next slide. And just end by thanking everyone for the support for the NQI and the bills that are coming. I've seen a lot of the work that's gone in, and I think they're really smartly targeted and intelligent. And let's keep that going. These larger centers are critical. Quantum computing is still a heavy research area, exploring applications now as well, but those longer duration programs, large centers, really are incredibly valuable to not have too piecemeal of the programs, because it's just harder to have an impact in quantum. So the coordination across agencies, I've seen it increasing the last 5 years at an incredible pace. So it's wonderful to see that going. So thank you all, and have a great day.